Recording is rolling on Tuesday, September 21st. You guys just saw a polycube with a bed of nails. Now, how many guys have been on a bed of nails? Who's been on a bed of nails? Ooh, bunch of guys. I think he's got one over in Orlando. Again. So, what's the idea there? You guys learned a little bit about pressure. You guys remember doing the Pythagoras cup and whatnot? Talk about pressure being in either pounds per square inch or newtons per square meter, called pascals, all that stuff. Would you rather lie on a bed of 1,000 nails, or would you rather lie on a bed of one nail? What sounds better? 1,000. Yeah, let's go with 1,000. And this ratio spells out why. Because your weight represents the force pushing down on those nails. And the area that it's on, well, if it's like one nail, isn't that a tiny, tiny area? Which would that represent a huge pressure? That would puncture your skin. Versus if it's like 1,000 nails, that's a 1,000-fold area, which is actually a much smaller pressure. So you're actually better off having more nails. And if you had like 1,000,000 nails, it wouldn't even feel like nails. It's still like a metal surface. And so, actually, I originally just had this for my honors class, but I figured I'd show you guys real fast first. So I'm showing them a hydraulic lift, which involves something called Pascal's principle. Actually, I'll read Pascal's principle straight off Wikipedia. It says, I can do that now. The principle in fluid mechanics that states that a pressure change at any point in a confined incompressible fluid is transmitted throughout the fluid such that the same change occurs everywhere. Okay. Or what matters for us is that, do you guys think that the pressure is the same at an equal depth all the way down near the bottom? What if you go up a little bit? Is the pressure the same at this depth all the way across? Yeah. What about, is the pressure the same here as it is over here, same depth? Yeah. What about the pistons that are about the same height? You think the pressure is the same pushing up on those pistons? It sure is, but that has an interesting consequence. If the pressure is the same, what that means is that you can, with a very small input force, lift something that's very heavy. I'm going to do a little bit of math related to that. So, Pascal's principle, the pressure on the left side is equal to the pressure on the right side, the pressure pushing against the bottom of each of these pistons. Okay? And, well, to lift a car, would you need the force acting upward to be equivalent to the weight of the car, hold it in equilibrium? Okay? So, see, pressure is force per area, so that ratio is the same on both sides. Okay. And I threw some numbers up here. Now, since I'm just trying to skirt you guys through this real fast, I'll just go ahead and flash the notes up here. But what have we got here? We've got a car that weighs 20,000 newtons. And look at the size of the pistons compared to each other. See how it's 10 square meters compared to 1 square meter? Right. 1 square meter, that's about 9 floor tiles, about, right? Pretty close to. And this one's 10 times that. And the ratio is what matters. So if you plug in those numbers, I got a 20,000 Newton car on a 10 square meter area. Right? That ratio represents the pressure pushing up on it to keep it in equilibrium. Right? And on the other side, I've got some input force to lift that car. It's on 1 square meter area, so a very small area. And if you solve for that force, it ends up being only a tenth of the weight of the car. The car weighed 20,000 newtons. You only need 10,000. You only need 2,000 newtons. That's a tenth of that to hold it in equilibrium, or maybe like push it up at constant speed. Guess that? Right? Interesting. Now, you don't get something for nothing here, and the way you pay for this is in terms of like the distance it moves. But would you guys agree that if you're pushing the piston on the left side down, it's displacing some volume of water, and that volume of water gets pushed over to the right side? Right? And those volumes are equivalent. The volume down here is equal to the volume up here. Right? But then when you go back and divide by the area, that means that the height change for the car is going to be very small. You know what that's also very similar to, and we haven't quite gotten to this part in the class yet. We won't for a few more weeks, but we're getting there. You guys remember this pulley system here? I've got a very small weight that can actually lift something that's heavier than it, gets a mechanical advantage. But the way you're paying for it is, look at the distance that small weight moves versus the distance that the large weight moves up. Right? You guys see those distances are definitely, right? The small weight moves a long distance just to lift the heavy one a little bit. Okay? So when we get to conservation of energy, I'll have you guys do a whole lab that looks pretty similar to that. Right, so much future content, but yeah, it's similar to this hydraulic lift. Right. All right, so that's all a side note. We get you guys rerouted to HP stuff. Right. Well, some follow-up from yesterday. You guys remember yesterday I took you guys through a ranked choice simulation, so I wanted to give you guys the results. You guys voted for Mr. Ortiz, as did most of my classes. And once I did, Mr. Ortiz was second. So I went ahead and checked the box next to his name and submitted that, in case you're curious. It's on there. Yesterday I took you guys through these first 5 problems, and well, today we'll do the other ones, and then you'll at least have the basic homework out of the way. Of course, you guys got many other problems you can pick from that the solutions are also out there. I should say this too, which is that I wrote the solutions about 2-3 years ago, and I didn't realize the rules for free body diagrams at the time. So my free body diagrams are a little bit, they don't have like the central dot and the connected force vectors of the tails, so they're not exactly drawn correctly, but all the answers are correct. Yeah, you're gonna say?
Do we get extra credit for doing like some of the bonus or all?
Well, yeah, you gotta do all of them. Yeah, so if you do all these and then turn them in, then I will give you those extra points in the book. You got all that extra practice too. Nice. All right, so let's pick up from yesterday. Now I know yesterday at the end of class, where is it? I have this drawn out. Did I write it down here? There it is. Yesterday at the end of class, we did one that looked kind of like this, except that it was a 30, 60, 90 triangle. So I changed the angles a bit, but I gave the same weight. Remember, it's like a bird feeder pulling down. Now, because that was at the end of class, and also because this is pretty fundamental, good problem to be able to work through, let's actually sort of redo that. We're going to do it with just like a little bit different geometry. So let's say we've got the same bird feeders we had yesterday, but maybe the cables are a little bit different angles. Still a right triangle, so I guess that's kind of nice. Can you guys solve for what is the tension in each cable? So I'll have call it tension on the left and tension on the right. Okay. See if you can stay ahead of me. And if you follow your notes from yesterday, if you have them side by side, then you should be able to do that. You should be able to stay a step ahead of me through this whole problem. It's definitely something that you should be able to do from an AP class. And so I'm going to take these cables and draw force vectors over them, like tension forces. Right, so I know that the one on the left is going to be greater magnitude than the one on the right. So I'm going to draw it that way. Here's the tension on the left. Here's the tension on the right, which is not going to be as much as the tension on the left. How do I know that? Well, from teaching this class many years, but where that would give away, see how I made the tension on the right less than the tension on the left in terms of magnitude? You would really know the answer really stands out once you break these into components. Remember that's part of the problem? Because for this whole system to be in equilibrium, which if it's at rest, it definitely would be equilibrium, right? Zero net force. There has to be zero net force both in a horizontal and a vertical direction. That's why I made this Cartesian system. See these dashed axes, x-axis, y-axis? Okay. Those don't exist in real life, but they help you analyze the problem. So how much is the one up and to the left pulling? Well, it's kind of pulling up and kind of pulling to the left. How much up? How much to the left? Well, that's where we're going to break this into components, which you guys have been doing for a long time in this class. Even before I taught you guys kinematic motion, I taught you guys how to break forces into components, or, vectors into components. These are force vectors, tension vectors. Right. So there's up to the left, here's up to the right. See like that? We do need some angles, so I bet these angles are going to come into play. If you guys follow, you guys, I'm sure, figure out that this is 36.9 degrees right here, and that this angle is going to be your 53.1 degrees. Think about hard enough, you guys can figure that out, right? Some geometry. Okay. And now here's how I knew that the right tension is going to be less than the left tension. Because look horizontally. See how the right horizontal component and left horizontal component are exactly the same magnitude? Because those are the only horizontal components going on, so they have to cancel each other out. Okay? And then everything follows from there that the tension on the left side must be the greatest force. Okay? And then how about the two upper components? Those, I should say, the tension on the left is going to be greater than the tension on the right. The two upper components, don't those have to balance out with the 100 newtons pulling down? Okay. Now, if you want to write this out properly, then you would say that, let's see, the, actually, let me do a little bit more trick before I go write equations. Okay. This side right here, I'm going to call T left times cosine of 53.1 degrees. This right here is going to be T right times cosine of 36.9 degrees. This upper part is T right times sine of 36.9 degrees. And this one here is T left times sine of 53.1 degrees. Okay. You guys see why I chose those angles, right? You guys remember what those angles are about? What does angles correspond to? What triangle? 345. Okay. So I can actually take the sine and cosine of these crazy angles and represent them as fractions. Like, for example, sine of 53.1 degrees, that's 0.8 exactly, well, nearly exactly. So I'll call that 4/5. So this is equal to 4/5 of tension on the left side. Cosine of that angle ends up being 3/5. That's what 0.6 is, right? 3/5. So this is 3/5 of TL. This right here would be 4/5 of TR, tension on the right, and this would end up working out to be 3/5 of TR. Okay. So in terms of fractions, which I don't know, maybe that looks a little cleaner. And of course, we've got the weight, 100 newtons acting straight down. Okay. We don't know what the tension on the left or the tension on the right are. Okay. All right. Now let me start making a system of equations. I know that the sum of the forces in the x direction must zero out. Therefore, 4/5 tension to the right minus 3/5 tension to the left must zero out. Okay. And I also know that the sum of the forces in the y direction must zero out. Therefore, the 2 up must cancel with the 1 down. So 4/5 TL plus 3/5 TR minus 100 newtons must zero out. 0 newtons. Okay. This is my system of equations. System of equations. Okay. 2 equations, 2 unknown values. See, I don't know the tension on the right or the tension on the left, but they each show up in each equation. So that is solvable. Now, there are different ways you can solve systems of equations. There's substitution, there's elimination, there's matrices. Let's do substitution. I think it's the easiest way to solve it. Hey, couldn't we get rid of the fractions really fast by multiplying everything by what? 5. Let's do that. So I'm going to say, bring these down here. I'll say times 5, just to get rid of that fraction. So therefore, tension on the right, well, 4 times that, minus 3 times the tension on the left must zero out. And 4 tension left plus 3 tension right minus, and 100 times 5, that'd be 500 newtons. Must also zero out. Newtons. Okay. So got rid of the fractions. Hey, this looks like a much nicer problem to solve, doesn't it? That's why I chose those angles that we started with. This crazy, like 36.9 degree angle. That ended up creating really nice looking numbers, doesn't it? Okay. So this is still a system of equations, just manipulated a bit. Okay. I'm going to take this top one and rewrite it. I'll solve for one of these in terms of the other, so I can do a substitution. So maybe I'll solve for tension on the right side. So I know 4 times tension on the right side must now be equal to 3 times tension on the left side. Divide both sides by 4. I can say tension on the right side is equal to 3/4 tension on the left side. Okay. Where I still don't know what either of those tensions are, but I now do know what the relationship is between them. I know that one of them is 3/4 of the other one. Okay. So I have an expression that relates the 2 tensions. Now I'm going to take this and substitute it right into there. Substitute. Okay. So I took this top line, solved for one terms of the other, and now I'm going to substitute that value into the second equation. Okay. You see that? I mean, this is just a math process at this point. We've done left physics a while ago. We're just doing algebra review at this point. So now I've got, see, 4 times tension left, like left tension. That's like your X value in algebra, plus 3 times the right tension. Now the right tension, I'm gonna replace with this expression, 3/4 of the left tension. Minus 500 newtons is equal to 0 newtons. Okay. You guys good so far? Now I have one equation, one unknown. Oh, I can just go solve for that, like it's solving for x. So 4 times what I want, plus, that looks like 9/4 times what I want. Well, that's going to be equal to 500 newtons. Add that over. Okay. So what is 4 plus 9/4? That is 6.25. So, yeah, 6.25 times tension on the left side must be equivalent to 500 newtons. Divide both sides by 6.25. And the tension on the left side is exactly 80 newtons. So we've got one of the tensions, but I'm still curious to know what is the other tension. So we know this one's 80. So what's this one? Well, I can very quickly get it by going back to this expression that I used to substitute before. Remember this expression that I circled that relates the two tensions to each other? That's the perfect point to go back to, because I know the left tension is 80 and the right tension is 3/4 of that. So tension on the right side is 3/4 of tension on the left side. We know that from before. Just substitute that in. Put that right in there. What is 3/4 of 80 newtons? That's exactly 60 newtons. So tension on the right side, therefore, is 60 newtons. There you go. That's it. All right. Take you guys through that one more time. Let's take a look at these notes so you guys can digest this. All right, there's 100 newton pulling down. We got 2 tensions pulling at these particular angles, which the sine cosine values worked out to these very nice fractions, like 4/5 and 3/5 kind of thing. Okay. Then we had to set up a system of equations. Say, well, the sum of the forces horizontally and also vertically have to zero out. So these 2 guys horizontally must zero out, and these 3 parts vertically, this, and this, must also zero out. Then you have a system of equations, 2 equations, 2 unknowns, and probably the easiest way to solve it is with substitution. Not the only way, but one way. So get one tension in terms of the other, substitute it, then you have one equation with one unknown, and you can solve for one of the tensions. Then go back to that substitution expression, plug in the known value to get the other one. Boom, boom, done. Guys good? All right. What's next find? We got number 25 coming on up. Number 25, which was, I got that right.
Wait, what number is the problem we just did, or is it?
We just did number
19.
19. Now, yesterday in the class, I used the same angles, but I changed the weight of the bird feeder. And today, well, I did like a double manipulation, but I think that was worth going through again, because that's a pretty good problem to know. Like, if you can handle that, then you're really good at forces and vectors. Okay, number 25, a bucket of this given mass full of water is raised by a rope. The upward acceleration of the bucket is so many meters per second squared. Can you find the force exerted by the rope on the bucket? Ooh. So this is not equilibrium. This bucket is accelerating. That means that there is a net force on the bucket. I'm going to do a free body diagram where we got a bucket. Maybe it's got an old classic handle on it. Okay, so center mass of the bucket, something like this. Now, let's look at the forces on this bucket. Well, if it's accelerating upward, shouldn't the force from the rope upward be more than the weight of the bucket? So I'm going to draw it that way. I already know that the force from the rope must be greater than the weight of the bucket. Probably exaggerated a little bit, but gets the idea across that that force is greater than that force. Okay? what were you given? You were given the mass of the bucket and also the acceleration of the system. So I'm going to make up my own numbers. There's, hold on, hold on a minute. Oh, here we go. Okay, so suppose I have a 8 kilogram bucket, and maybe the acceleration of the system is 2 meters per second squared upward. So those are given values. Can you find the force from the rope? So there's what you know, there's what you want to know. It's our goal. All right. This definitely looks like a Newton's second law of motion, doesn't it? So net force is equal to mass times acceleration. And net force, well, that's just the difference between what's up and what's down. So this net force is the force from the rope minus the weight of the bucket. It's equal to mass times acceleration. Now, let's see, we're solving for force from the rope. So, hey, mg plus ma, what does this look a lot like?
Like the elevator?
Yeah, tension in an elevator cable. You guys remember that? Tension in an elevator cable? Or, for that matter, a normal force from a elevator floor acting up on a person. So, you guys might remember, well, this problem is not on AP's equations, which is something I want to mention too, but I did give it to you on this page that you've had since the first day of school. Forces, I gave you guys just a handful of formulas, and one of them is tension in an elevator cable right there, which is exactly what that is. We just re-derived it. Now, this is definitely something that AP could throw at you. There's like certain style questions that AP asks, like, can you solve it in 2 minutes? It does incorporate certain information. And I'll tell you that if AP does want you to solve something like this, they would want you to derive it from scratch. Could be that would be true definitely for an FRQ question. If it's a multiple choice, then of course you just bubble something in. So it might be handy to just memorize this form so you can just like solve it a little bit faster. But yeah, let's just plug in some values now. So we got 8 kilograms. Let's call it gravity about 10 meters per second squared. And it's accelerating upward, so that's why I'm doing plus 2 meters per second squared. It's that number. 8 times 12 is 96, so kind of ran out of room here, but force from the rope, therefore, is 96 newtons. 8 kilograms times 12 meters per second squared, that's 96 newtons. So 96 newtons up minus the 80 newtons down. Let's go through that way. Where's my calculator? So now that we finished this problem, we know that this must be 96 newtons. You guys know that the weight of this thing had to have been 80 newtons. Okay. So 96 minus 80, isn't that a net force of 16 newtons? Acting on a mass of 8 kilograms gives you an acceleration of 2 meters per second squared. Yep, we're all good. Guys good? Next problem. So, number 38. Okay. Actually, we look at these two right here, 36 and 38. You see 2 different designs of outwoods. So the one we're going to do is the classic double elevator outwood. 36, if you look at it, that's a modified outwood that has a horizontal component to it. Next couple of days, I want to give you guys the lab versions of these. So I debated over the weekend, should I do all the labs first, the book problems first? So I'm going to sort of spoil some of the answers to the labs, but when we go through it, then you see that the answers to the labs are going to be, well, you guys know how to solve it mathematically by then on paper. Okay. So I got 2 objects with given masses. Can you figure out the tension in the string, the acceleration of each object, and also the distance that each object will move during the first second of motion if it starts from rest? So one problem at a time. Actually, I'm going to solve them a little bit out of order. I like to solve for the acceleration first and then the tension after. I think there's a little bit different ways to solve it, but I'll just show you the way that I prefer to solve it. So I'm going to do that. Advantage of being a teacher. There's multiple ways to do things. You can pick the way that works best for you. You else got to figure it out. That's how it is. 38. So got this massless frictionless pulley, got a couple of masses connected by a string. A lot of times the book will specify a light string, and the implication is that the string is like massless, right? Otherwise it would affect the problem a little bit. You know what? Since you guys are AP, I'm going to solve this in terms of variables. Let's call this mass A and mass B. And maybe if we feel like putting in numbers, we can throw in some numbers later. But why don't you solve this in terms of variables? So let's look at free body diagram, which means we need some force vectors. So mass B, I'll make the heavier of the two. So I'll call this force vector mass B times G. That would be its weight, wouldn't it? Okay. And let's make mass A the lighter of the two. So I'll have a little tiny force vector. And call that mass A times gravity. That force vector. Something like that, right? And let's think of thought process before I start chugging away with a bunch of equations and stuff. Think about physically how this is going to work out. And same thing next couple days when you guys are put together things like this in the lab setting. I want to give you guys this pulley and some string and some weights, and you guys get to feel this out. If these two masses were the same number, let's say it's like 1 kilogram and 1 kilogram, what would the system be doing? Yeah, it would be not accelerating. There would be no net force. And if it's at rest, it would be at rest. Something like that, right? What if you went to the other extreme condition? What if you put all the mass on one side? How would the system be accelerating? Wouldn't it be perfect free fall? Yeah, it sure would be. This is one of these good tools that you can add to your mental toolkit. It's something you can get out of a class like physics is, can you play around with variables? Can you take things to extremes, look for boundary conditions, turn variables up and down? Yeah, so you guys know that one extreme, this could be the same mass, and there would be no acceleration in the system. And furthermore, the tension in the string holding them together would be exactly equal to the weight of either one of them. The other extreme condition, you could put all the mass on one side, the acceleration would be perfect free fall, and the tension in the string in that case would be 0 if all the mass is on one side. Okay. Let's go add the tension vectors, because you probably have something kind of in the middle for these outwards. Do you guys think that, hey, isn't mass B going to accelerate downward and mass A is going to accelerate upward? Which means that the net forces must also agree with that. So if there's some tension in the string that's tying them together, this tension better be, I'm going to call it a Goldilocks force. It's got to be bigger than the small weight, but smaller than the big weight. I'll call it T for tension. Right? See how it's going to accelerate mass A upward, but it's going to accelerate mass B downward, the net force is it.
Is the tension the same on both sides?
Yeah, the tension is the same. Because one string can just have one tension in it. Isn't that true? As long as this pulley is massless and frictionless, right? that would be the case. Yeah, it's the same tension all the way through. Yeah, that's a good thing to point out too. Right? And that's something else we're going to have to solve for. What is this tension? Okay. So let's solve for the acceleration of the system first. What is the acceleration of the system? And to know that, you have to say, well, what forces are actually relevant into Newton's second law of motion? Because they aren't all relevant, but some of them are. This weight here is an external force. This weight is an external force. External because it's Earth's mass pulling each of those masses towards it. So it's like from the outside. But the tension is internal to the system. Either way you look at it, internal force. Right? Which means that it's not driving the system to move from the outside. It's not going to be incorporated into Newton's second law of motion. It's just holding everything together. Kind of like if I have this pen and I move this pen around, the force from my hand is causing the pen to accelerate. But what about like this point right here accelerating? Well, isn't it really being pushed around by all these plastic molecules that are holding the pen together? Yeah, but that's just internal to the pen. That's just internal to the system holding it together. Right? So it's not an external net force. So for Newton's second law of motion, we care about these two weights, and the tension we'll worry about later. So Newton's second law of motion can have acceleration of the system is equal to net force divided by mass. And I'll say total mass. Richard? That's, okay, so that's just Newton's second law of motion. Well, let's plug in some values. So net force. Wouldn't these two weights be acting kind of like people playing tug of war? So this weight on the right side says, let's turn the system clockwise. And the weight on the left side says, no, let's go counterclockwise. And they're fighting each other, right? Shouldn't the net force just be the difference between those two? Yeah, so I should say mass B gravity minus mass A times gravity. Okay, that weight minus that weight. That's what the net force is. And what is the total mass that's being moved around? That's to say, what's the total inertia? What do you guys think should go in the denominator?
Add it together.
Yeah, just add them together. Add them together. Add the two masses. Like that. Right? Okay, so let's see, we're subtracting in the numerator, but adding in the denominator. One reason that makes sense is because remember the forces up here, and these forces are vector quantities, so they can like add or subtract. They have directions associated with them. Versus mass, like inertia, well, that's a scalar value. So there's just some total of it. You just add it up like absolute value type thing. Remember a few minutes ago, we were already playing around with boundary conditions. We were saying at one extreme, these could be the same mass. And if that were the case, there would be zero acceleration. Let's see if this is consistent with that. If they were same mass, they'd be the same weight. The numerator would be zero. It would be zero divided by something. Wouldn't that be zero acceleration? Hey, that checks out. Right? And the other boundary condition, the other extreme, that's to say, would be if you put all the mass on one side. Now, if you do that, it should be perfect free fall. Let's see if it is. If it's all on one side, it'd be something minus zero divided by something plus zero. It'd be basically the weight of something divided by its own mass, because the other piece would just be zero. Oh, and that would just be G, wouldn't it? Would it just be perfect free fall? That's exactly what that would be. So yeah, this definitely checks out. And if you like, here's the answer to one of the parts of you guys' upcoming lab. So spoiler alert, but here it is. You could also factor out a G and get the difference of the masses divided by the sum of the masses. Yeah, all times gravity. It's that ratio of gravity. And this is bounded somewhere between 0 and G. So acceleration of the system is somewhere between 0 and G. Okay? That's good? Your textbook also gave you some numbers. So I'll make up my own numbers. Let's say that mass B is like 9 kilograms and mass A is like 8 kilograms. Now, if that's true, 9 kilograms versus 8 kilograms, is the acceleration going to be closer to 0 or closer to perfect free fall? What do you guys think? Yeah, closer to 0. It's probably going to accelerate very slowly, isn't it? Okay. Let's try this out. Acceleration of the system with those numbers. I've got 9 minus 8 over 9 plus 8. The kilograms are going to cancel. All multiplied by about 10 meters per second squared. I wonder what that's going to be. 9 minus 8 is 1. 9 plus 8 is 17. That's 1/17 of Earth gravity, which is 0.59 meters per second squared. Yeah, between 0 and 10, where 10 meters per second squared would be perfect free fall. This is definitely a lot closer to 0, isn't it? It's just like you guys said it should be, because those masses are very close to each other. You guys good? Number 46, a hockey puck is struck by a hockey stick. It's given an initial speed v0 in the positive x direction. The coefficient of kinetic friction between the ice and the puck is mu k. I'm so sorry, guys. Let me go back. I know I was forgetting something. It's scratch that. Right. We forgot to get, or I forgot, I should say, get the tension in the string, and also how far did it move in like 1 second, something like that. Let's just go with these numbers, and then we'll just continue that using these numbers. We still got, oh yeah.
When the question asks the acceleration of each object, is that the same as that, or?
Yeah, okay, that's a good point too. The textbook does specify acceleration of each object. Now, don't they have the same magnitude of acceleration? just different what? Directions. So you say the heavier one is going to accelerate down, the lighter one's going to accelerate up, but it's with the same number, same magnitude. Yeah, that's a good point. Oh, now the tension should be the same regardless of which block you look at, but to get the tension, what you want to do is focus on one of the free body diagrams. You can pick either the left block or the right block. I'm going to do both side by side to show you that this does in fact work out the same either way. Okay. So I could look at the left block and say that there's, well, I'll just play off this number that's already here. Let's just continue with numbers. There's 80 newtons of weight acting down, and there's some mystery tension acting up that, well, I know it must be more than 80 newtons, but that's all I know. Versus I could have picked the other block, and I'll do that over here. So the heavier of the two blocks, which must have the exact same tension pulling it upward as the white block, but a much larger mass acting down. Well, it's too much. It's larger than the tension. My example number was 90 newtons, like that. Now, either way that I solve this, I should get the same number for the tension. And it goes back to Newton's second law of motion. Net force is equal to mass times acceleration. Except this time I'm not looking at the system from a macroscopic point of view. I'm looking at just individual blocks. Okay. Net force, shouldn't that just be the difference of the two forces? So on the left side, I've got tension up minus the weight down is equal to the mass of the block, which is 8 kilograms for the left one, times the acceleration, which came out to be this number, 0.59 meters per second squared. That's actually a little bit rounded, so these tensions might be very close to each other, but maybe they're off by like a Newton or something. I don't know. We're going to find out. So that works out like that. And then the one on the right, well, the net force would be, here's what I'm going to do. I know the one on the left was accelerating upward, the one on the right is accelerating downward. I'm going to change the definition of what's the positive direction. I'm going to say that the net force is the difference of the weight and the tension. And that's equal to mass of the block, which is 9 kilograms, times the acceleration, which is also 0.59 meters per second squared, except this time you know it's downward. So sort of side note here, on the left side, I'm defining up as the positive direction. And on the right side, I'm defining down as the positive direction. In case you're looking at your notes later and trying to figure out exactly how all the negative signs go and how it works out. It's a little bit different perspective here. But I can just finish this out with algebra, and I should get the exact same value for the tension either way. So on the left side, I've got 8 times 0.59. Actually, let's see exactly what the acceleration was actually 0.588 something. I'll take that, multiply by 8, add 80, and I've got tension on the left side is equal to 84.7 newtons. How about the right side? Well, here I have to do a double swap algebraically. Add the tension over, subtract this over. What is 90 minus 9 times 0.59 meters per second squared? I'm getting the tension must be equal to 84.7 Newton. Hey, that's the same force. That's the same force. So either way you do it, see how physics is always self-consistent, right? Internally self-consistent. Okay, there you go. Furthermore, that tension is the Goldilocks force, just like we said from the start it should be. It's more than the small weight, and it's less than the big weight. It's between 80 and 90 newtons. Okay. And there was one last part to that. It says, how far does the system move? Well, they said either block, up or down, in 1 second. Doesn't that sound very kinematic? So they gave us a time, and you know the acceleration, and you're trying to figure out how far, and it's starting from rest. Which one of these is that going to be? First, second, or third? Yeah, first one. Okay. How far is a function of time? That's definitely the first one. Okay. And then starting from rest, I can use a simplified form. I can say that however far it goes is 1/2 AT squared. Okay. Of course, one block's going up, one's going down, but they have the same distance. Okay. So that's 0.588 meters per second squared for 1 second. Square that. So let's just work out to, that is 0.294 meters, because all the seconds cancel, and the distance it goes is that many meters. About 29 centimeters. Hey, 29 centimeters. That's almost the same as the length of this ruler. And so if you had exactly those masses, and you hook that up to that red pulley, okay, and you let it go for 1 second, it would go about the length of this ruler. There you go. Okay, now we're ready for 46, the one with the hockey puck. Right, so draw this out. I was starting to read that before, and then it says hockey puck is struck with an initial speed in the positive x direction. You draw this hockey puck from the side. There's a hockey puck, center mass. Got one so far. We strike it to give it an initial velocity. So it calls V naught, initial velocity. The coefficient of friction is given as mu sub k. Can you find an expression for the acceleration of the puck and also the distance that it slides, only in terms of given variables? So your given variables are, you know, the initial speed of the block, you know, coefficient of kinetic friction, and you're also allowed to know Earth gravity. A lot of times when AP wants you to do what we're about to do, which is solve in terms of variables, they will not mention Earth gravity, but sometimes you need it. So the way they phrase it is like, and any physical constants as appropriate. Whenever you see that phrase on an AP FRQ, a lot of times it means there's also a gravity field. Okay. You're given that. Those are all our given values. Notice what was not given. The mass of the puck. Right. The mass of the puck was not given. I bet it's going to cancel out at some point. I mean, that's a pretty common thing to happen in this class, right? We're supposed to find two things. Can you figure out the acceleration of the puck? And isn't this going to be probably a negative number? It's like slowing down. Right? And also, how far does it go before it comes to a stop? We'll call that distance d. So with those given values, can you find those things? That's all you know. That's it. And really, you know nothing because there are no numbers. It's all variables. So let's do a free body diagram. FBD, free body diagram for this hockey puck. Well, I bet it has a weight that's pulling it straight down. Call it mg. I bet there's a normal force from the icy surface holding it up. I'll call that normal force, okay, which is also equivalent to mg, isn't it? Happens a lot if it's just a level surface and nothing crazy going on. Okay. Which direction is the friction force? To the left. Because if it's moving to the right, then friction, the kinetic friction must be opposing that. Now, if this puck is on an icy surface, do you think that the friction force is a very large or small magnitude?
Small.
Yeah, very small. Like icy is not very much friction. So I'll draw it that way. I do. Friction force friction. Okay. Can you guys eyeball that and just estimate, supposing my numbers are correct, my vectors? What's a pretty good estimate for the coefficient of friction?
Quarter.
I like a quarter. Yeah, maybe this is about a quarter of this, like 0.25. Right. I'm sure ice is slippier than that, but you guys get the idea, right? This compared to this. Okay. Right, so we're going to figure this out. Acceleration. I bet we could use Newton's second law of motion and get acceleration. Can we do that? Let's start with that. So, draw my graph down here. Acceleration of the puck is equal to net force divided by mass. There's Newton's second law of motion. Wait a minute, they didn't even tell us the mass. Well, I bet it's going to cancel out. We're going to find out. Hey, what is the net force on that hockey puck? Just the friction, because the other two cancels out vertically. The only force is the horizontal force. Right? So the acceleration must be the friction force divided by the mass. But hey, you guys know what? You guys have an equation for friction force. If it's sliding, it's equal to what? Coefficient of friction times normal force. Okay. This is on your AP equation bank, sort of. It's here near the top. They express it as an inequality because if it's static friction, then it can build up to that point. But if it's kinetic friction, actually you can change that to an equal sign. You guys remember doing that? Okay. So that's on your AP equations. It's also one of the formulas that I listed in this cell right here on this page. So you have that in a couple places. You've had that for a long time. So I'm going to substitute that. I'm going to take this. I'm going to substitute right into there. So now the acceleration of the puck is equal to coefficient of friction times the normal force divided by the mass of the puck. If you didn't see where we were going with this before, I bet you see it now. Because normal force, I can substitute out with what? mg. This is equivalent to mg right there. Yeah. So now the acceleration of the system is coefficient of friction times mg divided by m. It doesn't matter what the mass of the puck was. It's going to slow down at a rate of whatever the coefficient of friction is between the ice and the puck times the gravity of the planet. Ooh, now we can play hockey on Mars. Yeah, you guys that? That's it. Has nothing to do with mass of the puck. What about this? What if you took a big old crate and you put a crate right on top of the puck, and you got it into motion with the same V naught? Do you think it would still slow down at the same rate? Yep, because mass canceled out. And we still have to figure out how far it goes, some distance d. Do you think that's also going to be the same? Yeah, because mass cancel out. So that's the other thing we have got to figure out. How far does that puck go before it comes to a stop? Ooh, does that sound like a job for the three amigos? I think it does. Which one is going to take us home? Figure out how far it goes to come to a stop, if you know the initial speed. I like the third one too. Hey, remember, this third one doesn't mention anything about time. So yeah, that was a great one. So let's do that. I'm gonna go final velocity squared is equal to initial velocity squared plus 2ax. That's just copy pasted, but maybe we could modify that for those. So I know it's going to 0 meters per second, coming from some general initial speed. Remember that's one of the given values, right? Some V naught was a given value. Now here's where I want to modify this too. If you push it in a positive direction, but it's also slowing down, you know it's slowing down because friction is slowing it down. I should really slap in a negative sign right here. I'll say minus, I'll go ahead and just handle that right there. Minus 2 times, and then the acceleration, I'm going to substitute in coefficient of friction times gravity. So this is coefficient of friction times gravity. That subscript on the coefficient of friction has been k because kinetic, right? So mu sub k, it's Greek letter mu, coefficient of friction. And this is all times some distance. Now, if you're going all the way to 0 meters per second, that's where it would stop. That means that the distance we're solving for is the full distance, like the stopping distance. Okay, is that? All right, we're really close to solving this. So remember, just for your notes, mu g, the same thing as a. Okay, so just do some algebra. Maybe add this term over. So I'll get 2 times coefficient of friction times earth gravity times the sliding distance is equivalent to V naught squared. Then divide both sides by this coefficient, and the stopping distance must be equal to the initial speed squared, all divided by 2 mu g. And that is the answer. So recap this real fast. You were given these values. You want to figure out rate slowing down and how far it goes. Set up a free body diagram and Newton's second law of motion. Then just start making a series of substitutions. The net force in this case is represented by the friction force. The friction force is coefficient of friction times normal force. Normal force is equivalent to the weight. Mass cancels out. You get this expression for how fast it's slowing down. And then go back to kinematic motion, last topic, to figure out how far it goes. That's it. That's the whole thing. Now, there is one thing that I want to look at with this. Look at the relationship between the starting speed and how far it goes. Notice that is a squared relationship. So, for example, what if you kicked it twice as fast? Well, what happened to its stopping distance? 4 times as far. What if you tripled the initial speed? 9 times as far. In the future, when we do conservation of energy, this is going to come back. And here's the story that's going to be attached to that. You're driving a car. You triple the driving speed of your car, and then you hit the brakes. By tripling the driving speed, what happens to your stopping distance? It's going to be 9 times as far. So you guys will see that in the future from a different point of view.